Assignment 17, 3.2, difference quotient. And one definition of derivative. Nothing is really new in this lesson. And we're just going to formally define a few things and build off of everything that we've already learned, but not much new here. Actually, I don't think anything. I might show you one thing, but it basically comes from Algebra 1. So, let's start with our essential question. How do you use the definition of derivative at a point to calculate the value of the derivative at that point and confirm your answer algebraically and numerically. Okay, so we've already been doing a lot with the difference quotient, but I'm going to go ahead and formally introduce it to you. So the difference quotient it's basically, so if I have this graph, let's see, let me just come up with a graph here. X-axis, y-axis, and I've got some curve. And let's call that C. This is X. So then on the y-axis, this will be f of C, and this will be f of X. We've already been using the difference quotient to find the average rate of change. So and another word for average rate of change is slope, right? So if I was trying to find the slope between these 2 points, then basically I was going to do f of X, right, change in Y, minus f of C all over X minus C. Okay, so we've already been, nothing new there. So then, and I've already alluded to this in the past, when we talk about the derivative, well, derivative is not average rate of change, it's instantaneous rate of change. So that's where it's happening at an instant. So this time right here along the x-axis needs to get smaller and smaller and smaller. It basically needs to go to 0. So we call the derivative the limit of the difference quotient as the denominator goes to 0. And then we'll formally define derivative at a point. So derivative at a point, and we'll let that point be x equals c. So f prime of c, that's how we denote derivative. Oh, here, let me underline this. So f prime of c, that's how we say the derivative of f at c, will equal the limit as x goes to c of basically that difference quotient. Okay, so this basically means a couple of things, a couple of really important things. The first part is that this is going to be the instantaneous rate of change of f of x with respect to x at x equals c. The second really important thing to understand is that when we find this derivative, or f prime of c, it's going to be the slope of the tangent line at the point x equals c. Okay, so if you think about making that tangent line, right, that if you think of drawing, or maybe with my ruler I can do it. Think of drawing that tangent line. We'll pretend like that's touching it. Right, it's going to give you the slope of this tangent line whenever x equals c. Okay, so the f prime of c is going to be the slope of the tangent line at the point x equals c. Okay, we're going to do an example from your book. So page 76, number 4. I'm going to flip my page over. So our example will come from page 76, number 4. So, of course, number 4 is going to have lots of different pieces to it. Okay, so for problems 3 and 4, you've got a, b, c, and d, and this is our equation down here, our function f of x. So, we're concerned with when x equals 6, and the first thing we're going to do is we're going to use the definition of derivative to calculate the value of f prime of c exactly. All right, so let's start with the fact that we know that f of x equals negative 0.2 x squared, and we care about the fact where c is equal to 6, or on the x-axis we're looking at x being 6. All right, so we're going to calculate f prime of c as the limit as x goes to c of f of x minus f of c all over x minus c, that being the difference quotient. Now let's apply it to this actual problem. So what we care about is the derivative when x is 6, so f prime of 6. And that'll be the limit as x actually goes to what c is, and c happens to be 6, of f of x minus f of 6, f of x minus f of 6, all over x minus 6. Now plugging the actual function in, we're going to have the limit as x goes to 6 of what f of x actually is, negative 0.2 x squared, minus what the function is when 6 is plugged in. So that's minus a negative 0.2 times 6 squared all over x minus 6. We'll simplify that a bit. The limit as x goes to 6 of negative 0.2 x squared, that becomes plus 0.2 times 6 squared Now I see that I have this x minus 6 in the bottom, and I'm wondering if there's a way that I can reduce that, because right now if I plug 6 in here, I'm going to have a 0, and that's not going to be okay. So I'm looking for something that maybe I can factor out. It looks like I can factor out a 0.2. And I might even want to factor out a negative 0.2 so that then I'll have x squared minus something else squared, which is a difference of 2 squares. So the limit as x goes to 6, I'm going to factor out that negative 0.2, which will then leave me with x squared minus 6 squared, or 36, all over x minus 6. So the limit as x goes to 6 of negative 0.2, factor that, I get x plus 6, x minus 6, all over x minus 6. So now my x minus 6's reduce. This is just the limit as x goes to 6 of negative 0.2 times x plus 6. And if I evaluate that, I'm basically just plugging 6 in right here. So that'll be the negative 0.2 times 6 plus 6, or negative 0.2 times 12. 12 times 2 is going to be 24. Put that decimal in there, so I've got negative 2.4. Negative 2.4 then is the instantaneous rate of change at x equals 6 of this function. So really it's the slope of my tangent line right at x equals 6. Moving on to B, it asks us to plot the difference quotient in a window that includes C and sketch the result. So we're really going to plot a function, a new function that we've created by finding the limit as x went to 6. So we created this new equation right here, which if I simplify that becomes something like, let's call it y equals negative 0.2x minus 1.2. So this here is a linear function, right? So I took the derivative of a quadratic function and I ended up getting a linear function. So this is the line that we need to plot with its window including C, which happened to be 6. So I'm going to use graph paper for this. And again, I'm just plotting y equals negative 0.2x minus 1.2. And originally, when we found the limit, the number that we had to plug in was 6. So our output at 6 is going to be negative 2.4. Now, the problem right here is, before I put my dot down, let's remember that, is this function actually even defined at 6? It's not, right? It's got a removable discontinuity because I factored out an x minus 6 on top and was able to simplify. Okay, so really we cannot plug in a 6. If we did that, this thing would be undefined. So it's undefined at 6, meaning I've got a removable discontinuity at about negative 2.4. Another point that we could use to help us graph this would be maybe the y-intercept, negative 1.2. And so there is my graph. Okay, now C and D I'm going to do on the same graph. So I'm going to make this graph really beautiful. So first of all, C asks you to plot the graph of the function in a window that includes C. So I need to actually plot the graph of my original function. And this is a parabola, and it's opening downward. So a parabola opening downward, it didn't look like it had an H or a K, so that means that it's basically going through the origin, so I don't care much about my positive y-axis. So I know it's going through the origin, opening down. If I were to plug in, 1, then I'd get negative 0.2. If I were to plug in 2, I'd get negative 0.8. So I'm going to just choose a couple of these points. Actually, why don't I go ahead and put that into my graphing calculator? I'll get some good points, and then I'll also have something to check with. So going to y equals negative 0.2 x squared. And let's get some good values for my table. We can start at 0, sure. So I'm not going to do every single point here, but how about if I do at 2, I'm down to negative 0.8. How about 4? At 4, I'm down to negative 3.2. And then how about at 6? Negative 7.2. Okay, and it's a parabola opening down. So something like this. And then it would be symmetrical on the other side. And if you don't believe me, why don't we graph the whole thing? Right? Their graph definitely looks better than mine, but that's just how it usually goes. I'm pretty used to that. Let's just try our best, because we don't really care about the left side. We care more about this right side. Somehow, though, my left side looks better. Okay, so now for D. So I'm also going to do D here. So it asks us to plot, oh, you know what I should do is I should label this line. This is f of x equals negative 0.2 x squared. Okay, so through this line, they ask us to plot a line through C f of C with slope f prime of C. So C f of C happened to be here, right? Right, I plugged in 6, and I would get negative 7.2, I think is what we ended up with. Okay, so right here I'm going to plot my tangent line, which should have a slope of negative 2.4. So this point here was 6, negative 7.2. And from there, if I go down using my slope, or my derivative, 2.4 over 1, then I'm going to end up at negative 9.6 when I get to positive 7 here. So that's another point that would be on this line. Okay, so I'm going to go down 2.4 from here so that I'm down at negative 9.6. And I'm going to go over 1. So my tangent line, trying to be as close to it as possible. It's hard though with a pencil. Looks like that. Okay, now let's talk about the equation of this tangent line. Okay, so let's find the equation of the tangent line. So let's see, let's write that here. So we know the slope of it. We also know a point, that point where it's actually tangent to the original function. From there, I can figure out what my y-intercept would be, or I could have used point slope form. So if I were to draw this all the way up, it would have a y-intercept of 7.2. So the equation of this tangent line is actually y equals negative 2.4x plus 7.2. That was not asked of you to do. However, I'm just kind of introducing that to you because you're going to need to do this. Okay, so this is finding the equation of a tangent line going back to Algebra 1.